He obtained his PhD in computer science and engineering from IIT Madras in the year 2004. Prior to that, he studied MTech in industrial electronics from NITK Surathkal, the year 1997, and BE in electronics from Sri Siddhartha Institute of Technology, Tumkur, in the year 1994. So far, he has guided 21 PhD theses and 11 are still ongoing, the areas of speech and handwriting processing. He has published over 250 research articles in reputed Indian and international journals and conferences. He has executed large volume of funded projects and also provided consultancy to many public sector and private limited companies in the areas of speech processing. So today's talk is mostly on speech signal processing and its evolution in the conventional sense, especially with reference to Kipstrel analysis and linear prediction analysis. But as gradually been mentioned, even this domain is not is touched by the deep learning techniques and machine learning techniques. So, which essentially the representation of such speech signal is all called as representation learning way of building the applications. So today's talk will be focusing on both the conventional aspects of the speech signal processing as well as the artificial intelligence way of looking at the speech signal processing. So with that, we are thankful, especially for accepting our invitation in spite of his busy schedule. With this, I request Professor SRM Prasanna to take over the dais and start with the talk, sir. Thank you.
Thank you, Dr. Deepak. Thank you, Sibsankar Padi, for this opportunity. Is my slides visible?
Yes, sir. Yes, sir.
Okay.
It
recording started?
Yeah, recording has started, sir.
Okay. So how much time I have?
Sir, Sibsankar, Dr. Sibsankar.
Yeah. 1 hour, sir. It's total 90 minutes, sir.
Okay.
1 hour, 75 minutes, sir.
Yeah, you can utilize it for 1 hour 15 minutes, sir. So 15 to 20 minutes we can have for discussions.
Okay. Good morning. Thank you very much for this opportunity once again. I welcome all the participants to this ATAL program. Hope all of you will be significantly benefiting from the talks that will be delivered from different experts, both from India and abroad, what Dr. Sibsankar and Dr. Deepak are able to put together a wonderful program. So in this talk, I will be giving a bird's view of different speech signal processing methods that have been developed in the field of speech processing in the last 5-6 decades. Apart from in the last 1 decade or so, there is an effort to use deep learning models to extract relevant features from the speech signal by processing the raw speech signal waveform in a nonlinear way using deep learning models. So both these aspects I will touch. These are some of the standard references for the speech processing area. These are very classical books, which anyway will be available as slides you can go through. The other thing is there are 2 important references. One is Representation Learning and Review on New Perspective, which came in 2003 by Yoshio Bengio, is one of the prominent personalities with reference to deep learning area. And just now, one paper has come by Siddiq Latif, etc., et al., where they have explained about deep representation learning in speech processing, challenges, recent advances, and future trends. So apart from the traditional material, I have also looked into these 2 articles while preparing this talk, while preparing for this talk. These are some of the important books for the broader area of pattern recognition, under which all this pattern recognition, machine learning, and deep learning comes. We have this classical book by Duda Hart on pattern classification, then a classical book by C.M. Bishop on pattern recognition and machine learning, book by Professor Egnarana on artificial neural networks, then Michael Nielsen, neural networks and deep learning. It's an open book. Similarly, Ian Goodfellow, Yoshua Bengio, and Aran Corville, deep learning from MIT Press. Then Charu Agarwal, neural networks and deep learning. And there are good NPTEL course by Dr. Mitesh Kapra from IIT Madras, deep learning part 1 and 2. And finally, Ali Godse, deep learning, University of Waterloo course. I have organized the presentation in the following way. I'll introduce to this direction of work, and I will highlight the importance of speech signal processing by taking some thought process from how humans do speech processing. That comes under speech processing in humans. Then the whole domain of speech signal processing may be treated as mimicking the human way of speech processing. So we have the whole speech signal processing sub-discipline in this broader speech processing area may be viewed in two verticals. One is feature engineering, which essentially deals with exploiting all the latest developments in signal processing to the field of speech processing to extract relevant features from the raw speech signal. Alternatively, the another sub-discipline or vertical in the speech processing area is same for feature representation, can be treated as representation learning, where the goal is to again model features or extract features from the raw speech signal, not by conventional signal processing method, but by using different deep learning models. Then I'll summarize my talk. Suppose if we come to the field of speech processing, if you ask a question what it deals with, if you see speech processing essentially deals with all about speech signals and associated methods for processing them. If you have already done a course on speech processing as elective course in one of your studies, or you have taught as faculty members in different institutions, it will be easier to appreciate this point. Why this statement I am making here is we should not confuse this speech processing area with general communication. In the general communication also, one of the main message signal or modulating signal is a speech for long distance transmission. There, we don't really worry too much into internal details of the speech signal. We only treat speech signal as a correlated signal. How do I exploit this correlation present among the sequence of samples to compress the signal and transmit and reconstruct? Opposite of this is poking or going deeper into the speech signal to know what different informations it has. That is, the focus here is to extract and model information from speech signals. Then when you come to the definition of the word information as referred to speech, some of the important information sources in the speech signals are message. That is the basic essence for which we do speech processing. Even in human speech processing, when we generate speech and listen to the speech, the primary goal is to convey some information or message. Of course, apart from these, the speech signal has wealth of information, like you can know the language of the speech signal, in which language the speech signal has been generated. Because without the language information, we will not be able to decode the message part. We will also, the speech signal will also be coded by the color of the speaker. Color in the sense, the vocal tract, the system as well as the source of the speaker is unique. and the signature of the source and the system of the person who is producing the speech, which we call it as speaker, is also embedded in the speech signal. So that also we can find out. We can find out the emotional state of the person. We can identify the health condition of the person, etc. Different levels of rich informations are there. In speech processing area, our focus is to extract one or more of these message components and use that knowledge for any practical utility, any practical application. Vis-a-vis, if I go for communication, I don't care about these different information sources that are present in the speech. My goal is only treat speech as a correlated signal, try to compress it by extracting this correlation property. So, thus, in the speech processing area, since each of these message components are very important, because all these message components are being exploited by humans in human-human communication. Suppose if I want to establish a successful human-computer interaction or human-machine computing machine interaction, the computing machine also should be able to extract and model this information and use this knowledge while interacting with the humans. So accordingly, there are several subfields in the speech processing area like speech recognition, language identification, speaker recognition, emotion recognition, health condition recognition, and so on, which essentially focuses on modeling one specific information source present in the speech signal. Suppose if I build that speech recognition system, I can use that technology for communicating with humans. Humans can speak into the computing machine. The speech recognition system will convert that message in the spoken form into text in text in that language. So that is the reason why people are very much interested in the speech processing area to develop these technologies. If it will make life easier, that I don't have to type, I don't have to visualize the video terminal. I can just speak into the computer. This computer will listen to our speech and perform the required task. It will also give feedback in the spoken form. So as a result of that, we are left free with our visual systems as well as the hands to do something else. So that is the advantage of speech processing. Coming to the speech processing area, this area is there for last, at least electrical communication discipline, if you say, starting from 1960s, last 5-6 decades, a research community across the world working in this area. If you see all the efforts that have gone in this speech processing area, may be broadly classified in two verticals. One is the signal processing efforts for extracting relevant features from the raw speech signal, which is more commonly termed as speech signal processing. Second one is modeling the patterns present in the speech signal. That is by once you extract relevant features, with the help of relevant features, try to model the patterns that are present in the given speech signal. That field is called as pattern recognition, and the variants of that with more degrees of freedom and more powerfulness compared to the tools and techniques that were presented in the conventional pattern recognition are machine learning and deep learning. Now, people are talking about and also demonstrated their feasibility for feature extraction and modeling by deep learning. Even feature extraction is also being done by deep learning area apart from the modeling. So in this talk, I will be briefly mentioning about the different ways of speech signal processing, which one domain I call it as feature engineering, because we do a lot of engineering to extract relevant lower dimensional features from the given raw data, raw speech data. For example, we can do time domain analysis to extract some gross level information from the speech signal, which is also being useful for many tasks. Similarly, we can do short-term Fourier analysis, which is a variant of conventional Fourier analysis that we have studied. Of course, short-term Fourier also we might have studied, which essentially takes care of the time-varying nature or non-stationary nature of the speech signal. Then we have specialized speech analysis technique like Epstein analysis, linear prediction analysis, and sinusoidal analysis, which are specifically developed or tailor-made to the speech processing area to extract relevant features from the speech. Coming to the representation learning, all the deep learning based methods to extract and model features from the raw speech signal, that comes under this vertical of representation learning. Of course, it is better before directly jumping into what speech signal processing methods we are using, and the questions that crops up in our mind is why the feature engineering was not sufficient. Why do you go by deep learning? Uh, those questions will crop up. Is it the reason just that deep learning is the latest trend? That's why we want to try this speech signal processing also by deep learning, or something else? To do that, we need to at least give some reference to how humans interact with the external world. Of course, humans interact with different sensory mechanisms. At least when I take the speech, how we produce, perceive, and process speech signal in human cognitive system, that will help us to appreciate the latest trends of representation learning in deep learning. Why I am saying this statement is the speech signal processing methods that have been developed, which are grouped under the feature engineering, of course, they are very good. They have proposed or given excellent algorithms for extracting features from the speech signal, and also being used in practice in many speech applications like mobile phones and other devices, even general telecommunication. However, there is more to be done when I want to extract features from the speech signal. So that is where the latest deep learning based approach, which we call it as representation learning, has a role to play to extract the features from the speech signal by processing the speech signal in a non-linear manner, and also not prefixing and telling the computer to look only for those features and extract and throw away all the remaining information. This representation learning will process informations at different levels. So as a result of that, in a nonlinear manner, as a result of that, it may be able to capture more information which is not directly amenable to digital signal processing. So that is where now, to appreciate that, I think we should just spend few minutes on how humans interacts with the external world, and how attempts have been made in the literature to mimic that activity on a computing machine. For example, if I take humans, we all interact with the external world by 5 senses: auditory mechanism, visual perception mechanism, smelling, tasting, and touching. So these are the windows through which we view or interact or interface with the external world. So now what will happen is, suppose if I'm listening, that is auditory perception mechanism, I sample the external world through these ears, and then whatever the sampled information will, from that sampled information, I will try to extract from relevant information to be sent to the cognitive system. That relevant information is called as representation. So pass on the representation to the brain via the sensory pathways. For example, when we are all listening, our ears will convert the incoming acoustic pressure variations into equivalent electrical variations, which more commonly termed as bioevocative potentials. And then bioevocative potentials are transmitted via the auditory nerve to the human cognitive system or brain or higher centers of learning. Suppose if you see, if we have a mechanism to record the bioevocative potential that are being evolved or generated on the auditory nerve fiber and match with the speech signal, it will look like a much smoothed version of the speech signal. Okay, so under that condition, that means to say the whole varying the speech signal, time varying speech signal, which is shows such a random variations, will not be passed on as equivalent same random variation signal to the um, higher centers of learning. Only a representation will be passed on. That is an equivalent of feature engineering that we are doing on signal processing. Now, if you see the whole process that is happening in the ears, there is no FFT there, or there is no conventional short-term processing or anything. It goes through a non-linear way of processing by the inner hair cells, basilar membrane, and so other things. So which says that what we are doing using digital signal processing is good, but it is not penultimate. Okay, so that is where there is a scope for going through a non-linear way of signal processing. That is where the representation learning comes into picture. If I go for pattern way of processing, this is one thing. Representation learning by humans is one way of passing on lower dimensional information through sensory pathways to the auditory, central nervous system. Second thing is, this is yet another hallmark of humans. Human brain processes everything as pattern way of processing. This distinction I will tell later. That means to say, human's brain does not take only a set of numbers, array of numbers, 1D, 2D, or 3D dimensional arrays, which we use for processing speech, image, or video signals on a computing machine. That is not the way how human brain processes the incoming information from the five senses. Okay, and whatever it will do is, it will do it in the form of a pattern. For example, when we eat mangoes, we have a specific taste. On the other hand, when we eat grape, we get some other specific taste. Suppose this has been learned over time. The taste of mango is a pattern. The taste of grape is another pattern. This pattern is distinct compared to the other pattern. Now, that is, suppose whether you eat one grape or one mango or a bunch of mangoes or half kg of grape together, even one piece is sufficient for you to say that no, what I am eating is this particular fruit. And that is what is called pattern. So in pattern way of processing, the amount of data for testing, it can be very small also. Even if there is a piece of information, I am able to robustly say what is that pattern is. Okay, and the taste of grape is one pattern, the taste of mango is another pattern. And that is how, of course, while learning this, we have several sessions of exposure. I have eaten mangoes over years. Based on that, I have developed a taste, which is a pattern for mangoes. Even when I say, somebody says mango, I think some of us, all of us, most of us have got an image of that in our cognitive system, what the taste looks like. That is what I call it as pattern. Humans are able to interact with the external world and sustain and interface with the external world, mainly because of this representation learning and pattern way of processing. Okay, then all this happens under the supervision of the cognitive system, that higher centers of learning are human brain. The cognitive ability is yet another important aspect of human brain, which will do, of course, we will say no, is a central nervous system and centralized processing happens in human brain. But the human brain has the capability through its network of nervous system to make any activity both centralized as well as decentralized. For example, if it is a active, just a caution, I am not an expert, but I'm hypothesizing like that. So a well-coordinated activity from the human brain happens so fast, it almost looks like that activity is decentralized. I was telling in one of the previous talks that when we are driving the car, when we become expert drivers by driving over many years, Then the way our right leg handles the brake, accelerator in manual driving, it looks almost like, it is not like a cognitive activity and are decentralized to the leg. Okay. Whereas it may be happening that the central nervous system is being so spontaneous in transmitting the information, but that intelligence of cognition is also being decentralized. That is what I am hypothesizing. The next part is the selective attention. We all have been blessed with this ability of selective attention. Otherwise, it will be impossible for us to stay in this world. Even in speech communication, if you go to a party, you will have hundreds of people in the party hall. If you just, as soon as you enter, you feel like a commotion there, then you will not be able to tolerate that commotion unless you don't have this hallmark feature of selective learning. Selective attention means I go and immediately get into a small group of my close friends. I start chatting with them. As soon as I start chatting with them in the same commotion, I can only interact with that small subgroups, and all that commotion goes into the background. And that is the ability of selective attention. Even this can be attributed, this cognitive ability can be attributed for all behavior of humans. Okay. For example, if I have a deep pain in a particular part of my body, if only I focus on that particular part of the body, 24 hours I am occupied by that pain. Alternatively, I say that no, it is not going to be possible. I have other works to do and start working on that. The effect of that pain subsidizes because you are not paying attention. Suddenly you start paying attention, again that pain comes to the top. That is what is that selective attention, another hallmark ability of humans. And also the whole interaction with external world, it is not that no, it is endowed in my body. When I after I took birth, I learned all these things. The all mechanisms required to acquire this has been embedded into our gene structure. Okay. As a result of that, when we come to this universe, quickly we are able to adapt and get all that information. And also, all these sensory mechanisms are evolved in nature and passed on in the gene format to the next generation. They are well optimized for maximum information exchange with minimum effort. Okay. The way human ears have been evolved in nature in such a way that they have maximum sensitivity to the human speech signal that have been generated. And the next level is the auditory signal, the music signal, audio signal, which is up to 20 kilohertz. And we don't hear anything below 20 hertz or above 20 kilohertz. So you can see the why that has happened is because one of the major activity of human perception system is listening to the speech signals of my own speech signal as well as when others talk to me. That is where this maximum information exchanges takes place. Now, these are the important parts we should appreciate, which we all have been endowed with. Since it is available free of cost endowed in our human bodies, we don't pay much attention to that. It is such a sophisticated system. And what we are trying to do with the development in technology is only try to mimic some of these. But of course, even though we experience all of these activities, we really do not know how exactly is being done in all aspects. Of course, some of them we have decoded to some extent, where beyond ambiguity. However, in many cases, we only are witness to that, but not sure how it is happening. Okay. So that is why I'm telling is when this digital signal processing came about 3-4 decades back, everybody jumped on that saying that, no, that is a great thing. It will solve all the problems in the world. Now the representation deep learning has come. The same trend we have moved into that level. But if you see, all of them are very brittle compared to what our human cognitive system is endowed with. For example, if I go for mimicking human interaction in computing, we felt, okay, our human ears have the ability to convert the acoustic signal, form of the speech signal, into bio-evoked potential. Can I have a sensor which can mimic this activity? That is where the concept of microphone was evolved, where you convert the acoustic signal, which is non-electrical, into electrical form. If you say, okay, then microphone has mimicked the ears, no. It has only just mimicked the operation of the human ear. It is not a very sophisticated thing when you consider how the human ear works. Human ear mechanism is much more sophisticated, complex, and non-linear way of processing the information. But the microphone is just a simple device which converts given non-electrical form of the acoustic signal into some equivalent electrical variation. Beyond that, it will not do anything. What it says is, yes, you have still scope if you want to work in the sensor area for improving the way we sense the speech signal from acoustic form to equivalent electrical form. That is the microphone. Coming to this, then, since we are mostly do digital processing on a computing machine, we need to convert the output of the microphone. It will be essentially analog signal. If I want to convert into equivalent digital signal, I need to sample that signal. So that sampling, we have this well-known sampling theorem. Essentially, the crude way of sampling is you sense at regular intervals of time, and that is called a sampling process. Of course, by some sampling theorem statement objective, we have sense, what is the rate at which sense, all those things we have studied as part of signals and systems course, as well as communication. This is nowhere as sophisticated like our human way of representation learning. The next one after sampling is what we call analog to digital conversion, which take the sampled value, quantizes it, and encodes it. That is analog to digital conversion. Once you have the digital signal, you do the signal processing, which essentially do pre-processing. Pre-processing means some sort of filtering to remove unwanted components, then do feature extraction, essentially to learn the relevant features for further processing. Essentially, when I consider feature extraction, one of the objective is to extract wanted information from the speech signal for a given task and neglect all other things. Pre-processing is without worrying about which task you are doing, the general other information that are stored in the speech signal other than the speech can be eliminated because of transmission, everything. There may be degradations and those things, or emphasize few frequency components in that. All those things can be done there. If you see starting from sensor to signal processing, everything is embedded in human ear. Okay. So the human ear, starting from outer ear, middle ear, and inner ear, all this activity will happen. Of course, there is nothing like a sampling, because we are just mimicking that activity to get a lower dimensional data. But human things works in a continuous domain itself, but they have many more sophisticated way of learning the representation compared to what we do by conventional signal processing method. Then, coming to the pattern recognition, modeling and recognizing patterns. So here, when I say pattern recognition, this is a term which is introduced in the field of computing when humans took the mimicking human way of interaction with external world, with human way of interaction with computer. They felt that the data processing is not the way. If you want to deal with human way of processing, we need to model what are called patterns. So that is where the concept of pattern versus data processing came into picture. We need to appreciate this point, pattern versus data. I already gave some example what is meant by a pattern. The taste of grape is a pattern. The color of rose, red rose, is a pattern. The way how I get a feeling that this is a rose versus this is some other jasmine or something. How do I get that mental concept of what is called a particular object, entity, or concept? That is called as pattern. Whereas in a computer, whatever you feed and process, everything is in the form of data. It is no set of numbers. Either it will be one-dimensional array, two-dimensional array, three-dimensional array, or n-dimensional array. So that is where we need to distinguish between pattern versus data, because all computing happens via data processing, whereas all human way of processing happens pattern way. This is another contribution by closely observing the human way of interacting with the external world, and this area of pattern recognition came into the field of computing, which essentially deals with modeling and recognizing patterns. Whether you take speech, music, image, video, or any signals you take, whether it is natural or man-made signals, if it is exposed to humans, humans always look for patterns in that. Without the concept of pattern, they will not be able to model the information, and also they cannot use that modeled information for later recall or recognition. Okay, that is where the pattern way of processing comes into picture. And then when researchers quickly realized that we need pattern way of processing if I want to interface natural signals or man-made signals into computing machine, they evolved several tools and techniques, and they are all housed under this topic called pattern recognition. When I come to the pattern recognition field was developed, people felt that when I go to computer, at the lowest level, the architecture of computer is stored program and data concept. So you need to store the data, what you need to process, and you need to write a program which has a sequence of unambiguous steps, which will, once you run the program, it will take the data, process the data according to the sequence of steps written in the program, and then generate the required outputs. So at the computing level, it happens as stored program, data, and concept. Whereas when I want to do pattern recognition, I need to build a layer over on that where I view it has looking for patterns, extracting patterns, and then modeling patterns, and use that modeled patterns for recognizing patterns at a later point of time. So that is how the tools and techniques were developed as well. So computer will continue to work on the stored program and data concept, whereas I build one more layer on that, which is I visualize when results are generated in the form of extracting and modeling as well as recognizing the pattern. What was happening in version 1 of pattern recognition? The process of discovering the patterns, modeling the patterns, and using them for recognizing the patterns. So everything was prefixed. That means to say, it is like if you see when horses which are used for tongas, they have been closed with some vision obstacles such that no, it has to focus only on the front to avoid any distraction. In the conventional pattern recognition tools also, it was like that. Only you look for this type of pattern. I am saying you that this is the pattern that may be present in the given speech signal. You don't worry. Even if there is something else also, don't worry. You just extract it. But of late, people thought, oh, this is too much restriction. Rather than that, I should give the flexibility to the computing machine to automatically discover the patterns. I don't say you will only look for this pattern. I only say there are different patterns in this, and you discover yourself. That means to say you are given one sort of degree of flexibility or automation to the pattern discovery process. And that is why the name machine learning has come into picture. In the case of machine learning, what we do is the learning algorithm is endowed with the capability that given data points, it itself will go and discover available possible patterns in that and model them and use it for later pattern recognition tasks. And there in the conventional machine learning, what used to happen is there is a freedom or flexibility for discovering the patterns, whereas the features extracted from the raw signal are still going by feature engineering. And this sort of flexibility that came for machine learning made the application of machine learning much wider. It need not be just limited to speech, music, image, biomedical signals, and video. It can be used for many more synthetically generated data, like any digital data that you generate, like digital transactions in the banks or digital transactions in the um, uh, chain of showrooms. So all these things which do not have, no, it's not naturally generated like human process, but still there also they have some trends. These trends can be treated as patterns. There is no domain knowledge like speech processing area has a domain knowledge for 2 centuries. We don't have domain knowledge for them. And also their interest for discovery and modeling the patterns is only short-lived because the technological trends will change, the way people will do the transactions will change. Accordingly, we may have to move on to the new way. So that the other thing is, when the pattern recognition field was introduced long back, at that point of time, the amount of digital data available for pattern modeling and recognizing was very limited. Then we had the luxury of manual analysis, careful analysis to see what trends are coming based on that, what model I can fix onto that. Whereas now with lots and lots of digital data being available, that we don't have that luxury of doing manual analysis of such a heap of digital data. That is where this automating the pattern recognition process for pattern discovery became very attractive. That is where this field of machine learning came into the picture. Then people felt that why this feature engineering is still to be gone to be dictated by the signal processing, because when I go for signal processing, it is essentially I'm doing linear way of processing the signals, which if I consider, suppose if I take speech itself, how the speech is being processed in a human ears, it is not exactly linear processing. Why are we not doing nonlinear processing? Because of the complexity involved in nonlinear processing, we are not doing. Whereas the deep learning models give a natural way of processing the data in a nonlinear fashion. I agree that interpretation is an issue. However, still we are able to do the nonlinear processing using the deep learning. So that is where we have, when deep learning trends came, people felt both feature extraction and pattern recognition can be automated. That is where the concept of deep learning became more versatile to be used in all areas of science and engineering. There are many applications like speech and audio, image and video, biosignal, etc. We can use it by this process. This general trending process are there. Of course, depending on what type of signal I am processing, the way of processing may change, but these general headings will be there. Sensor will be there, sampling will be there, analog to digital conversion will be there, signal processing will be there, pattern recognition will be there. Similarly, machine learning and deep learning will be there. Now, when I say representation learning, what we are trying to do is you process the incoming speech signal in a nonlinear manner to learn the lower dimensional information from the given raw data, which is higher dimension and much more variable, fastly varying data. Whereas we want to learn a nonlinear representation, and that is done nowadays by using the deep learning. Whereas when I go for earlier, when I was doing feature engineering by using signal processing, I am guided by prefixed linear processing. Whereas our human way of processing happens in a nonlinear and selective sensing. And that is what we are trying to mimic using representation learning using deep learning. Pattern recognition I explained earlier. So pattern versus data processing. And when 1970s, when this field came, pattern recognition, we were able to demonstrate, we were able to mimic on a computing machine the pattern way of processing, and also demonstrated that yes, we can also process the incoming data in the form of patterns, and demonstrated its feasibility. Only thing is, the limitation of this pattern recognition field at that point of time, when we consider now what is available with the deep learning and machine learning, it is guided by prefixed algorithmic steps, which essentially says it is blindly crunches the raw data and generates the features, and the pattern recognition step blindly models what patterns to be discovered and then use it for processing. Whereas the current trend is what we call end-to-end system using deep learning, which takes the raw data, first processes them to get the representations, relevant features in a nonlinear processed way, and then uses that feature for pattern modeling. This is a picture which I use it very often, taken from public domain, to illustrate the differentiation between then and now. For example, traditional machine learning means including the pattern recognition. We used to do like this. As human experts, with the help of a computing machine, you through the microphone get the speech data into our computer, spend a lot of time in analyzing that speech signal to see what is that unique feature that can help us to do pattern recognition. Based on that, you develop an algorithm and use that algorithm to generate the features, which is lower dimension. That features are then applied to traditional machine learning model for doing any classification task or something. Then use that trained model to do the classification during testing. Now we can see all these three modules have been clubbed into one deep learning, deep neural network representation. So what it will do is it will take the raw data and processes them in a nonlinear manner. First few layers will extract the representations, and then the representations in the later layers will be used for building classification boundaries. And then as a result of that, from input to output as you reach, you first learn the representation and then use that representation to learn the patterns. So the whole these three efforts, three modules have been merged into one deep learning model. Finally, the deep learning model will give you directly the classification output. Coming to the way of human-human communication, if you quickly see that, we are just focusing on the spoken language here, which is a verbal communication and oral way of communication. We also have non-verbal communication via oral way, but when we say speech processing, our just focus is on verbal communication, which is backed by a spoken language. That is what is our. There are other forms, I will not go into that. If you broadly see, when you are doing the spoken language processing, suppose we have a talker and listener, what we are trying to do is we take the message formulation takes place in the mind of the speaker, and that will descend into a neuromuscular commands, and our speech production system gets activated. Dynamics of the speech production takes place, which modulates the air coming out of the lungs and generates the acoustic modulated air comes out of our mouth and nose. That is called as acoustic pressure variation or the acoustic signal. That is what travels in this atmosphere, C, in the air, and then reaches the ears of the listener, that is ear, and which gets converted from acoustic pressure variation to bioechoed potential. From that bioechoed potential through the auditory nerve goes to the brain of the listener. If you see, origin and final destiny are in a cognitive processing, whereas the next change will convert that into mechanical vibrations, and then acoustic vibrations, then electrical variations, and again go back to the electrical form. So that is what it happens. This is, for example, if you see in the highest level of learning center, we have linguistic level. When I am producing speech, the language information is there in my cognitive system. Using that, I code my thought. That is that linguistic level in the brain. From there, it comes to physiological level in my production system. From the physiological level, at the output of the mouth or nose, we have acoustic level. And from the acoustic level, again, it gets back to physiological level when it is listened, processed through the human ear, and then goes to the linguistic level, to the brain. Okay, so that is what will happen. Then, by studying both production system and perception system, by different specialized areas in the speech processing, many important contributions have done by the digital signal processing. For example, just focusing on the production system, people have developed several mechanical models as well as the electrical model. This electrical model is important for us because if I go to all our mobile handset have been implemented with this model for both speech feature extraction as well as speech generation. When I am producing the speech, when I am speaking into my mobile phone, the microphone senses the speech signal, converts into digital form, and the digital signal is processed through a digital signal processing method called linear prediction analysis, which will extract the parameters of these different blocks of this model, which we call a two-state speech production model. Then only those extracted features are transmitted to the receiving point. At the receiving point, those parameters are plugged into this model and then excite this model to generate the speech signal. That is what happens in our mobile phone. And when we are doing this mobile communication, we need to reduce the data rate required for transmission. So that is why we take the help of this production model. So this is one of the greatest contributions of the digital signal processing area into the speech processing. And as a result of that, we are able to bring the dream into reality of mobile communication, where we use our mobile handset for spoken communication. Similarly, people have spent a lot of time to understand how our human auditory system works, essentially the human ear, functioning of outer ear, middle ear, and inner ear. So as a result of that, several interesting results have come. For example, if I take the speech signal, first the acoustic preservation will go here. We have this ear drum, which all of us, if you closely observe the ear, you will come to know that is completely blocked the outer ear to middle ear. And this ear is a thin membrane, it will vibrate when acoustic pressure variations impinges on it. And that vibration, again, that is nothing but a mechanical vibration. That mechanical vibration is transmitted into the inner ear, which is a fluid-filled chamber, which will convert into oscillations of the fluid inside the inner ear. These oscillations are sensed by the sensors which are lying around a membrane, which we call basilar membrane. And this basilar membrane is the one which will do a spectral separation, frequency separation of different components present in the speech signal. So depending on the area at which the sensitivity is increasing, so accordingly that frequency component is assumed to present. Accordingly, the bioequivalent potential based on that will be sent to the learning higher centers of learning. So for this point I've already told. Okay, let me see if there is any missing point here. See, earlier what we did was, by analyzing production, perception, everything, with the help of signal processing, we developed the two-stage speech production model, and by analyzing hypothesizing how human cognitive system works, we have done the pattern recognition. Now we are trying to do pattern recognition using machine learning and deep learning. The latest trends are in deep learning through. This one is important to appreciate because nowadays everybody talks about deep learning. If you see, you want to compare these deep learning trends with reference to the earlier trends, deep learning is mostly data driven. You need more data. You need the models are complex. You need more computing infrastructure, both software and hardware, much complicated programs, higher computing power. That is what I meant by computing infrastructure. But at the end, if you have all these parts, you have a large amount of data, you have trained complex models, you have computing software and hardware infrastructure, the resulting model will give you better performance. Okay. Whereas the good thing that has done with the help of deep learning is domain knowledge. This deep learning trend has become more domain agnostic. It is not mandatory. Hence, nowadays there is a lot of interest in developing speech technologies. Accordingly, several speech tech startups and companies have come. So it has moved from domain to domain agnostic. When I do by digital signal processing and conventional pattern recognition, it's dominated by the domain knowledge. I'm not belittling the importance of domain knowledge, but that type of domain knowledge requires a lot of time to develop any technology. Now, with the help of domain agnostic way, if some engineer just not bothered about the domain knowledge, he or she can go ahead and build the system. And now I told software means you need a a very complicated software program. Good thing is now a lot of open source toolkits are available. Then accordingly, open source toolkits are available, which enables us, you don't have to write anything from the scratch. You can just use that open source toolkit and run the program. And then you have GPU infrastructure available. You don't, even though it's costly, but you can rent it out also to run your programs. Only pay for your usage. So that way, even being in smaller places also, if you have interest, you can contribute. Of course, now if you see, data-driven is mostly industry-driven research, whereas domain-driven is academia research. Now, domain-driven also, we are slightly moving towards data-driven. Only thing is we are trying to play based on our interest, or we can say our way of doing R&D. We are trying to make a space for academic fraternity where our forte is in terms of exploiting the domain knowledge, whereas the forte of industry community is to build systems which are robust and work in practice. So now it will be like a complementary strength. So now, for example, any of my industry partners, if they say, okay, I have a much significant better performing system than what you do it in your lab. That is correct also. That is why we have commercially viable technology, but we can ask why it is working and what speech specific knowledge it has captured. They will say it's not of interest for them. As long as it works in practical conditions, it is okay for them. That is where our role comes, academic fraternity, where we can interpret the data processing that is happening in the DL models at various levels and explain that, okay, this is the reason why we are able to make the system work in a robust manner. And that is what is broadly comes under what we call the explainable AI. Okay. And so accordingly, industry community will work on developing technologies that are comparable to human performance, whereas academic community will try to interpret and understand and explain why that model is working. So, there are again psychoacoustics results which essentially dealt is a domain knowledge, essentially dealt with sound perception, where human subjects will perceive the sound played, which are designed and played, and based on their perception system, they will make their judgment and give the decision about that. And that has been exploited to bring out some important results. Based on that, good speech technologies have been developed. Where, for example, there is a well-known masking phenomenon in speech perception process, where you have a higher volume sound at a specific frequency, say in this diagram 250 Hertz. Then this large sound pressure level component will mask the perception of all the neighborhood components, provided those components lie below its certain preset threshold, which we call them as masking threshold. Say, for example, there is a contour here which shows a nonlinear way of dampening. It is maximum at this point and nonlinear way of dampening on either side. And if the neighborhood components in this area, if they fall below this line, then this component will not be heard when during the presence of this component. And this is called as masked sound, this is called as masker. So from speech signal processing point of view or feature engineering point of view, all these components are important. However, we even if you code and transmit to the receiving point or store it, when you retrieve and play it back to the humans, they don't perceive this sound because there is a masker present here. This is what is being exploited by MPEG audio coding to reduce the data rate requirement for storage compression. Similarly, we have a nonlinear, non-uniform filter bank, which is again mimicking the sensitivity of human ears, whose findings have been done through the psychoacoustics result, which is being well exploited, which we call MEL filter bank in the speech signal processing area. So there's that speech production model, two-stage speech production model, this masking phenomenon, MEL filter bank. These are some of few important findings from the speech signal processing and psychoacoustics, which have been exploited in speech signal processing in the traditional way to extract relevant features from the speech signal. And we have been found successful. But when I go for speech signal, when you process the speech signal through any of these signal processing tools and techniques that have been proposed, we assume a priori certain way of processing the data. You might have heard, if you are working in the speech processing, what we call segmental processing, where you chop the given speech signal into 10 to 30 millisecond segments and process each segment separately. Whereas the informations in the speech signal, which are important from human cognitive processing, are lying at much lower duration. That is as low as 1 to 3 milliseconds. I can have information which is crucial for human perception. Similarly, I will have information which is present at more than 100 millisecond region, which we call as suprasegmental information. Our most focus in speech signal processing is on segmental. And whenever you ask, why can't you use information from subsegmental and suprasegmental level, we try to make it as a very synthetic way of trying to extract, because it's very difficult to extract information from there. That is where, if I go by the deep learning way of processing, I don't process either subsegmental or segmental. Every sample sequence is given to the deep learning model. Deep learning model will, in a nonlinear way, combine information at all these three levels and try to model the information. So that is where the advantage of deep learning model comes into picture. Of course, I can analyze the speech signal by speech analysis technique, like it can be either time domain, where I plot the speech signal as a function of time, or frequency domain, amplitude versus frequency, time frequency analysis, amplitude versus time and frequency. I may be interested in processing the system information, vocal tract system information, which can be used for as feature vectors for speech and other tasks, speech recognition and other tasks. Spectrogram is one representation which we use extensively for amplitude versus time and frequency. Excitation source information is another information which is also equally important like vocal tract information, which together forms that natural speech what we are talking about. The phase information is also one important entity, which also contains discriminatory and important information about different speech components. Modulation features, the long-term variations of speech signals are also important. And then all these informations, whether it is vocal tract, excitation source, phase, or modulation, can be also extracted or modeled from the speech signal by representation level. These are some of the traditional way of processing the speech signal. For example, if I take the speech signal, plot it as a function of time, and you compute the energy of the speech signal, short-term energy, you get this contour. This contour helps me. The larger the value shows that this segment is more important. I can put a threshold here to identify where the speech regions are present and eliminate the silence regions. This is one of the important tasks we do, even in mobile communication. We don't want to just blindly code all segments. If it is silence region, it has no information to be conveyed for perception. Of course, At the receiving point, when you regenerate, I have to reinsert back the silence region. The duration is important, but not the uh, frequency component or excitation information there present. So accordingly, I can use the short-term energy contour for doing speech non-speech detection. Similarly, we have another important feature, short-term zero crossing rate, where you find out, since speech is a zero mean signal, you take zero as the reference line and find the oscillations around that. How many crossovers are happening? Zero crosses. That's why we call it a zero crossing rate over certain duration. Now you can see this is a very highly varying unvoiced sound, a fricative like. For that, the zero crossings are very large variation. So in that way, I can use this knowledge also to find out some consonant sounds like this. Of course, it will also help us to do speech transmutation in combination with the energy detection. Similarly, we have short-term autocorrelation. For example, given a voiced segment of speech or a periodic segment of nearly periodic segment of speech, I can use that, do the autocorrelation on that. When you see that, you get a peak, prominent peak at the pitch period associated with the human person. The pitch period is one important quality of human speech excitation, and this also being used for many analysis techniques. This also can be used for speech non-speech, voiced and unvoiced classification like that. So this can be done. These are all the three basic things. Suppose if I go for unvoiced sound equivalently and do the autocorrelation, you don't find a prominent peak there. Suppose I go and extract pitch contour for the entire speech signal, you see a continuous contour there which represent voiced regions, whereas the dotted ones represent the unvoiced region. There is no cleaning done here. So pitch is present only during the voiced segment. So in this way, I can do short-term energy, short-term zero crossing, autocorrelation, and then using them, I can extract pitch period information on the speech signal, and also I can do speech non-speech detection or voiced and unvoiced silence classification of the speech. These are two important tasks in the speech processing, which is being extensively used for communication purpose. Then coming to the frequency domain analysis, I can take a short segment of speech and then do the frequency domain analysis by using, say, short-term Fourier transform. Then I get the magnitude spectrum. You take linear magnitude spectrum, take the log magnitude spectrum, because if I go for linear magnitude spectrum, especially when I go for voiced sounds like prominent voiced sounds like vowels, the frequency components in the low frequency range, say 500 to 1500, will have very large amplitude. So accordingly, the higher frequency components are not visible. To make them, give them emphasis, we take a logarithm of that spectrum. Similarly, the unvoiced signal, where you have more emphasis on the high frequency component, taking logarithm, the lower frequency component gets emphasis. In case of silence region, there is no prominent component available. So in that way, by doing the frequency domain analysis, you can find out what is that different frequency components present in the speech. There is one well-known technique in speech processing we call Kepstral analysis, which is a variant of, we say, frequency domain, but it is almost equivalent like a alternative time domain processing of the speech signal. Take the speech signal, do a short-term windowing. Once I get a windowed segment, I do the discrete Fourier transform, frequency domain analysis, to get the spectrum of that. That spectrum, you apply logarithm on that. This is the most crucial thing of Kepstral analysis. The logarithm operation on the magnitude spectrum will essentially, if I take this x of omega, which is a product of vocal tract system frequency component and the excitation frequency component, which cannot be separated. On the other hand, if I take log on that, log A into B is log A plus log B. So now you made product into additive components. Once I have the additive components, I can separate out the frequency component. That is where I do the inverse discrete Fourier transform. When I come to time domain, in this Kepstral, naturally they get separated because of the additive nature in the log domain. So you get back the C of n, which is like a Kepstral we call, which is almost like a time, but it's not exactly time because I'm not recovering using both magnitude and phase, and also I have done nonlinear operation. If you have not done the nonlinear operation log and you are combined with the phase spectrum and take the IDFT, you will get back time domain. You are not using that. Since you are applying log on that, that nonlinear operation will move you away slightly from the speech domain that we call it as Kepstrom domain. And this Kepstrom domain, the beauty of this is naturally the slowly varying vocal tract information comes to the low Q frequency range and fastly varying components will go to high Q frequency range. For example, if I take a segment of speech signal, I have a voiced segment, windowed voiced segment, magnitude spectrum, log magnitude spectrum. Then you take the Kepstrom. This is how the variations will be there. You can see all this low Q frequency thing represent vocal tract information. This represent the excitation information. Whereas the unvoiced segment, if I take Kepstrom, there is no such prominent peak here. So in that way, only few components in the beginning will represent the vocal tract because all of them will be hovering around zero beyond certain values, say 15 values, for 15 indexes. Then those, even if you use the higher dimension, may not be of much use. And there is this MEL frequency capsule coefficient. I told that MEL filter bank is there. I just applying, instead of applying log, you also apply, first rearrange the frequency components on the MEL scale using MEL filter bank and then show that. And that rearrangement has shown that the capsule features that we extract by using MEL filter bank seem to be giving better information, better segregation of, better emphasis of the frequency component. So accordingly, consistently it has given good performance. That's where in almost all speech tasks, MFCC features have been dominating compared to the conventional capsule feature. We also can get the temporal variants of the MEL frequency capsule coefficients, which we call them as delta and delta coefficient. First we extract the MEL frequency capsule coefficient and then that original capsule features will come here, whereas temporal derivatives, if you take first order temporal derivative you take, you get delta features. Second order temporal derivative you take, you get delta features. Base features represent the static vocal tract shape. Delta will represent how the vocal tract shape is changing in that frame. Delta will represent how fast the change in the vocal tract shape itself is taking place. Okay. The other one important analysis is linear prediction analysis, where that production model I told, this H of Z represent the two-stage peak production model, which is represent. This A of Z represent the inverse filter. If you see the equation of the inverse filter, you have pth order FIR filter, where AK are the coefficients of that filter. These AKs are the coefficients that we extract by modeling the speech signal by using what is called linear prediction. With the help of a predictive process, we extract that relevant features. Once you extract the features and if you plot the spectrum by that, you get the smoothed spectrum. And these are the resonances of the vocal tract system. You can pick the peak to find out the resonances of the vocal tract system, which are more commonly termed as formant frequencies. It is also shown how, for example, if I take, as we increase the order of prediction and find out the error of prediction, which we call it as normalized error. If you 0th order means you are not done prediction, it will be 0. Then the prediction error falls down quickly for voiced segments because it's more correlated, relatively more correlated compared to unvoiced. When I go to unvoiced segment, it also decreases, but slowly, and it saturates at a much higher value. That means the prediction is relatively poor in case of unvoiced segment because it is less correlated. Similarly, there is a perceptual linear prediction analysis where, just like MEL filter bank, we rearrange the frequency domain information using some psychoacoustic results, what we call equal loudness pre-emphasis, intensity loudness conversion, all those things. Then you get back the signal into the time domain. Then you apply prediction on that. That is called perceptual linear prediction. If you see that in the FFT conventional MEL frequency capsule coefficients, once you get the magnitude spectrum, you apply MEL filter bank and take the logarithm and then DC to get MFCC. Whereas here, after get the magnitude spectrum, we go through other way of psychoacoustic result, Bark filter bank, equal loudness pre-emphasis, intensity loudness, then do the, coming back to the time domain, do the linear prediction and get the coefficients. Coming to the estimation of pitch, I can do by autocorrelation of the speech signal. I can get the linear prediction residual from the speech signal using linear prediction analysis, where the vocal tract information is filtered out. Then you get a much more prominent peak compared to autocorrelation of the speech signal. Or I can do Kepstrom analysis of that one. This is for the Kepstrom and this is for the autocorrelation. You can see either by Kepstrom pitch determination or by linear prediction analysis, you get a much more prominent peak compared to that. Then we have the pitch contours established by these three domains. You can see almost they're equivalent. Whichever is comfortable, we can use that. And if you see the short-term Fourier transform, which is a three-dimensional plot, we have one x-axis time domain, y-axis frequency domain, and the z-axis, the amplitude. You can see this speech signal, which is a time domain, two-dimensional signal. If you plot it as a three-dimensional domain, you get this hilly structures like this in the space, three-dimensional space. And that is where the information content is stored. As a function of time, all these hilly terrains are there moving. And that is where the information content of the speech signal is stored. Okay, this is what is being exploited by our human perception system to model the information. This we have mimicked on the computing machine to get that representation. Converting from 3D to 2D, we have this what we call spectrogram. And the spectrogram essentially from 3D we map to 2D to get the representations. Once we have these representations, either I can do by narrowband spectrogram or wideband spectrogram, depending on if I want to extract the excitation information, I can use narrowband spectrogram, or if I want to vocal tract information, I can use wideband spectrum. These are traditionally used for analysis by linguists to know what all the frequency components are the different sounds present in the speech signal. Okay, but we were not doing automatic processing of the spectrum. Nowadays, people do automatic processing of spectrum. This is one way, time domain representation of the speech signal. This is a two-dimensional time frequency representation of the same information that is present. And this is what is being used as a raw input for the deep learning model. Of course, we also have filter bank approaches for modeling the information, where you take the speech signal, pass it through different band filters, narrow band filters, and extract that information and use that energy as a filter bank energy for transmission. Of course, the number of filters will be much, much smaller than the total frequency bins. So as a result of that, this also, you can compress it better and send it to the receiving point for reconstruction. Even amplitude modulated filter banks are there to extract the filter bank and modulation components from the speech signal. And similarly, both amplitude and frequency based components can be exploited. So these are all the attempts that have been made by exploiting the developments in the speech signal processing area to discretely model different information components present in the speech signal. Whereas when I come to the representation learning, where we use deep learning models, we have the waveform and the corresponding spectrogram. We use this form of spectrogram as an image, speech as an image, and feed it as input to the speech signal. That we call it as a raw signal, and then do the representation learning. Suppose if you see the motivation of representation learning, what to learn in the representation is, we learn the image, that is the spectrographic representation, and also the sequence information, because in case of speech, both are important. The image representation as well as the sequence knowledge together will have a more robust representation for the information present in the speech signal. So here, earlier, we were using by signal processing, all those things I explained, Kepstrom, linear prediction analysis, modulation components by speech signal, they're all handcrafted features because I designed the algorithms. Whereas, and at that point of time, always this was a belief that a good set of features will give you good performance. And this feature engineering, as I explained, presented in the previous slides, gave so many important algorithms, people were very passionate about that. But now, these deep learning models in the recent trends have shown that you can learn better feature representation automatically, and you can further improve the performance of the deep learning based system. Suppose if you go for representation learning, the concept of representation learning is not just limited to deep learning models. We can have the sense of that in the earlier literature. If you consider principal component analysis, linear discriminant analysis, which are very basic linear algebra techniques, the process they do on the input data can also be treated as a representation learning. When we process the incoming raw data into a covariance matrix, we are not doing any Fourier analysis there. You just take the given raw data, do the covariance matrix. From the covariance matrix, you get the projection vectors or the principal components. And each of the principal components are weighted by their eigenvalues. Eigenvalues represent the quantification of that eigenvector. All these things, they process data and get that relevant information. That is one type of linear representation learning. Similarly, for linear discriminant algorithm also. There are nonlinear ones also we have proposed earlier for like kernel PCA or nonlinear, non-negative matrix representation. There are also nonlinear representation. Even neural networks which we were using in the earlier era, they were also nonlinear representations. So these traditional representations, this nonlinear feature they also showed, we can learn the representation. For example, there is one case in case of speech, what we call tandem features. You process the speech feature, that is MFCCs, through the neural network model. At the output of neural network model, whatever you get, that you use it as features for further doing speech processing tasks. Of course, there are some processing steps to avoid the skew distribution to convert that into GMM model suitable description. So the process of this channel is to convert the learned output from the neural network model, treat them as features for further learning. That is one type of representation learning. Even there are trap features where conventionally we do segmental analysis by taking a small segment. Here they took a longer duration segment for modeling the information by a neural processing. This is how we do neural processing to extract the. So in that way, long temporal context is also considered. That is also one type of representation learning. So in that way, the concept of representation learning is not new. Of course, people are not telling that as representation learning. With the deep learning, we are using specifically this nomenclature of representation learning. That initial results indicate that yes, if it is indeed possible, we should not be biased significantly by Fourier representation or Kepler analysis or linear prediction analysis, that this is the only way to extract features from the speech signal. However, we can do this nonlinear processing is deep learning models to extract the relevant features. That is what is being exploited in the deep learning model. In the deep learning model, first you take the speech signal, get its spectrogram, and use the spectrogram as a raw representation for the deep learning model and use that for extracting relevant features. For example, human experts are very good at finding out what are the sequence of sound units present in the visual representation. Since we are not being trained, we will not be able to say, but the trained experts, human experts, will be able to say what are the sequence of sounds present in them. The same thing we are learning through the deep learning model. Once they found that initially by using a conventional short-term Fourier transform based spectrogram, we are able to decode that information. People started working on developing different variants of spectrogram. This is by using Mel scale spectrogram. Then people use gamma tone based spectrum. Gamma tone is another filter bank by using psychoacoustics analysis. Like this, different variants came. Essentially, what they do is they redistribute the energy in the time frequency plane in a different way. So accordingly, this becomes different representations for the same speech signal. So you can use it for training or learning the representations. Of course, people have tried supervised deep learning by using any of the deep neural network, recurrent neural network, LSTM or gated recurrent neural network for modeling the representation. People have also tried unsupervised deep learning like restricted Boltzmann machine, deep belief networks, variational autoencoders, generative adversarial network, and deep autoregressive models to learn the representations. If you see now in the last decade, this deep representation learning itself has become one vertical in the deep learning area. One for pattern way of processing, the other one is for representation learning. With the help of this representation learning, you can do anything. You can do automatic feature learning, you can do dimensionality reduction, you can do data denoising, you can discover the clustering structure, you can learn disentanglement, you can do the abstraction of the information present. Like this, many tasks you can do in representation. It is not just explained only for feature learning, it can be used for many more tasks in the speech processing or any other pattern way of processing tasks. I have given details about this. In the interest of time, I will not explain all these things. So, of course, in the deep representation learning approaches, there are many approaches. We are comfortable with supervised learning, unsupervised learning. There are also techniques like semi-supervised learning, transfer learning, reinforcement learning. Even in transfer learning also, there are other disciplines like domain adaptation, multitask learning, self-taught learning. All these can be exploited. Different approaches for learning can be exploited for learning the representations. If you see what is that analogy I can bring for this deep learning based representation learning, I can treat that as a deep learning based expert system. In the earlier era, there was something called expert system or knowledge-based computing systems, where human experts' experience was coded in the form of a set of rules, and those rules will be coded further as programs. Then once the input data fed through that set of rules, finally it will say what is that information present. At that point, this was one of the hot topics in the artificial intelligence version 1, knowledge-based computing system. But quickly it was realized that even though it mimics that representation, the performance was not that great because humans are unable to explain all sorts of decisions they make. Whereas now in the deep learning based expert systems, what they first learn the representations from the raw data, and then that uses that representation further for pattern discovery, seem to be giving human level performance in many tasks, especially in the speech processing area, which has resulted in this end-to-end systems, which we call, and that can be treated as a deep learning. So if you say what is this deep learning model is now doing, means it is acting like a deep learning based expert system. So thus now representation learning that is being done by the deep learning model can be treated as a non-linear way of signal processing. Okay. Only thing is people are, when we are developing systems, people are just getting the representations and building systems. But what is required is treating that as a nonlinear signal processing area, we should be able to bring the interpretation for that the representations learned in terms of that repeatability and interpretability to be there for the representations, that we should be able to learn, interpret what is learned. And also it is exploiting the information from all levels of modeling when I'm doing the representation learning via deep learning. Of course, future we can look for how we can incorporate this selective attention in the representation learning. Of course, now when we are looking for speech, we are all in the speech processing area, we're using all this different deep learning networks, which will be dealt in the. Just as a final slide, if I see, we have this just one technology, automatic speech recognition technology. If you see, there is a steep decrease in the error rates in the last 1 decade, starting from 2012. This has been due to the impact of deep learning and also the complex architectures that are available in the deep learning. So which shows that deep learning seem to have given a good performance. Just to see, in case of speech recognition, the word rate has come down from 15 to 3%. Similarly, the speaker recognition rate, error rate has come down from 7% to 4%. Lower the value is better. Similarly, a natural sounding speech on a 5-point scale, the score is somewhere around 4.25 to 4.6. Even synthetic generated data like WaveNet also gives that equivalent performance, which all these different 3 important technologies performance by using deep learning methods indicate that the deep learning models indeed are learning good representations and they're discovering good patterns. As a result of that, we have good performance doing this. I think this I've already told. Coming to the speech processing, with these deep learning models available, we can try to attempt now higher level tasks in speech, like speech to speech translation, or intent recognition, or discourse identification, discourse recognition, or cognitive abilities. All these things can be done as a part of this. Just to summarize, I introduced all of you to the field of speech processing. The human approach of speech processing was initially explained to emphasize on the nuances and sophistication that is available with the human way of speech processing. Then I explained about the handcrafted features, capsular analysis, linear prediction analysis, and Mel filter bank and other things. Then explained about representation learning for speech processing, and different aspects of representation learning was highlighted. And I also mentioned what is the way forward for feature extraction. So with this, I'll conclude my talk here, and thank you very much. I took completely 1.5 hours of the time. If any of you are have any questions, I'll be very happy to take questions. Thank you.
Thank you, sir. Thank you so much. So you took us through the journey of speech processing, starting from temporal based processing to frequency based or spectral based processing, then introducing to the neural network architectures and how they've taken over those feature engineering aspect also, apart from those jobs that we were expecting. And apart, like you also have introduced us to perception and also the speech production aspects of the speech. This has laid a clean foundation for next subsequent sessions that has to be taken further. So with that, like audience, like if you have any questions, please, the forum is open. You can discuss with sir.
So good morning, sir.
Yeah, very good morning.
So this is Ramesh, sir, from IIIT.
Yes, please.
Sir, I think you gone through the speech recognition. So on which software we are going to implement this? Is it a MATLAB or it may be a software course like Python or Java? So which one we are going to use these type of speech recognition techniques?
Yeah. So nowadays, once these deep learning models came into speech processing arena, without exception, most of the attempts are using Python coding. Of course, as I told, lot of open source toolkits are available. That means to say, people have written open source toolkits for Python coding, and also modules they are making it available in the public domain. So without exception, it is Python coding.
Okay. So do we have any practice sessions on this topic, sir?
No, I'm afraid not, Mr. Ramesh. We don't have sessions for practicals or there in this FDP. It's more or less like to understand what researchers are doing and in what direction the research is moving. Of course, with some fundamental aspects. For practice sessions, we may have to have a different workshop altogether. In fact, we had one such workshop 2 weeks back. So I mean, a month back. That is IIT and IIIT Dharwad and AICSTEP, all three of us jointly conducted a workshop. So that's a different path altogether. Yeah.
Okay, thank you, sir.
Any other questions from the participants?
Hello, good morning, sir. This is Shravanti, sir.
Good morning.
This is Shravanti, sir, from RVR and JC, Andhra Pradesh.
Please,
Sir,
please.
Sir, I have one doubt, sir. Present, I am doing research work on ResNet model, sir. ResNet for the designing of residual layers, sir. Sir, can we use this model for classification of speech signals?
This ResNet model?
Yes, sir. ResNet model. ResNet 50 layers.
I think maybe it should be possible. I will request Deepak to answer that.
Yes, sir. Yeah, ResNet is also used for the classification purpose. So we can also use speech signal for such classification. Yes, it is possible.
Okay.
Actually, I am using this model for the enhancement of the speech, sir. So in that, the last layer is regression. I am doing regression analysis on this model. So can we use this model for classification? And can we extend my topic for the classification of speech?
Yeah, last layer has to be replaced from regression layer to classification layer. So
what about the preceding layer, sir?
Preceding layer, you can retain that now. You can retain that.
Okay, sir. Thank you, sir.
So there is one question in the chat box. Which one is better for speech recognition? CNN, RNN, DNN, etc. Deepak, you want to take that?
Sir, yeah. So mostly when we say convolutional neural networks, they essentially get utilized for deriving the bottleneck features from the neural networks itself. So post that, like we may have a fully connected layer like DNN for the classification purpose. That's how it happens. But as Prasanna sir rightly explained, the speech signal is a temporal based sequence. So whereas there is no much scope as far as the fully connected network is concerned to derive the temporal aspects in the given neural network. So that's where these time sequential networks like recurrent neural networks comes into picture. In fact, like we'll have one complete session on sequential networks itself, that is tomorrow, where I'll be explaining about the recurrent neural networks. Hope that question is answered, Mr. Mandar.
Yes, sir. Yes, thank you, sir.
Yeah. Sir, there is one more question, sir. Please talk about phonetics and phonology.
So, actually, see, we work in signal processing area. We are not experts in phonetics and phonology. Only we can know Deepak, if he wants, he can arrange a session from a phonetician. Essentially, it deals with, if you go for phonetics, you will deal with maybe Somudra Vijay sir in a session, maybe briefly touching about that. Just to give you definitions of that. Phonetics, essentially, when you take the speech signal, what is available in the speech signal as the acoustic evidence, you try to find out the sound units equivalent of that. Whereas phonology refers to a mental conception. That is, suppose this sound unit, what is supposed to come in a linguistic level, that mental pattern takes place. That is higher level of cognitive system. That is phonology. But once it gets manifested in the acoustic signal, due to co-articulation of the side sounds, adjacent sounds, the manifestation may be quite different. That is under the framework of phonology. Only this much I know. I think Deepak has to arrange a session for that.
Yes, sir. So I'm afraid we may not have scope for such a session in this FDP at least, but I will stay in contact with all the participants because we keep arranging the workshops and also some of these sessions. We'll keep you updated about that. So maybe post this workshop, we'll form a mail group or a WhatsApp group. So we'll keep intact and we'll work together in that sense. Yeah.
Deepak, there is a request from my side. One of you, if you share me the contact details of all these participants,
yes, sir.
We can create that national repository for the speech area.
Sure. We'll do that, sir.
Yeah.
We'll do that. Yeah. So also, can you put some light on speech enhancement using deep learning?
Yes.
Another question.
So, if you see in my one of the deep representation learning slide, there is one called data denoising. Essentially, the deep learning models can be used for when they process through when you take the raw data and process it through the model to get the final clean speech at the level. While training, I give exposure. Suppose if I take a supervised learning, you have the input noisy data and the corresponding clean data. And as you process, first representations are learned, and then finally the reconstruction of the speech signal at the final layer, matching with the original, I should be able to adjust the weights of the network such that I can give an input signal, noisy signal, it will finally evolve into a clean speech signal when it reaches the output layer. So that is what is being, or we can say autoencoder-like things, structures, where you have given, not autoencoder, hetero encoder, we can say. You have given noise vector and the clean vector at the output, it will learn the relationship between them. So accordingly, it can do the mapping. Or variation autoencoder. Many sessions are there where during training you have exposure to the pair of noisy data corresponding clean data. With the help of that, you learn the weights of the network in different manners and use that for reconstructing the clean signal. It is a type of representation learning only.
Yeah. Thank you, sir. Thank you for clearing most of the questions they had. So one more thing they're asking is the recorded video session. Dr. Sipshankar, can they access that recorded video later?
Yes,
Is
sir.
there a possibility? Yeah.
Yes, sir. So we are recording the video. So all the registered participants will get the link.
Okay.
Later.
Yeah.
And regarding attendance, we are taking. Of course, Google is taking care of that one. And just attending for, let's say, 5 to 10 minutes will not be counted. It's around 90-minute sessions. So just attending for 5 to 10 minutes will not be considered.
Yeah. Okay, Dr. Sipshankar. Thank you. Sir, thank you so much for clearing all the questions from the participants. In spite of your busy schedule, you made up the time for this session. We are thankful for that, sir.
Thank you, Deepak. all the best for the session for all the participants. Enjoy.
Thank you, sir. Thank you, sir. So we'll meet at 11:25, 11:20 to 11:25 somewhere. 11:30 the next session starts. Yeah. Hopefully all candidates will log in then. Thank you. Thank you.
Okay, thank you all.